Day. So, we are geologists. I'm Matthew, and this is Roberta, and this may look like a Cambridge lecture theatre, but no, when you walk through those doors at the back, you entered the time ship Geologize. And we are geologists, and we work for the Geological Survey Society. Ooh. And we travel across the UK trying to work out lots of things about rocks and how it all works.
Well, yes, and we've got to find out about the different rock formations and these rocks here at the front. We've got a new boss who's set as a task of finding out when and how these rocks were formed.
So, we built a time machine, okay? And we want to travel back and work out what happened to these rocks and maybe take some photos and a selfie.
It's really important that we get this assignment done because our new boss, he's a really scary guy.
Dear. Yes, and we're already on our last warning after I lost the priceless fossils. Our boss, Alan, he was furious.
And after we burst into song in the boardroom, he wasn't happy about that.
Yeah, he did not like that either. And we can't afford to get fired because we've got our student loans to pay off. So we're really glad that we've got all of you to help us. So are you going to help us not get fired? Yeah! I can't hear you. Excellent. Right, Roberta, are we ready?
We're ready as we'll ever be.
Okay, is the flux capacitor fluxing?
Yeah, I think so.
Oh, yes it is. Is the time rotor rotating?
Yeah.
Yes it is. And are the engines engineering?
Yeah.
Yeah, they are. Great. And most importantly, is the karaoke system online?
Testing. Yes.
Yes, good. We've got a karaoke system. That is amazing. And I've also put a cake in the oven because it's going to be a long journey and we may get peckish and stuff like that. So, are we all ready to travel in time?
I'll prime the ship.
Okay. Now, to start the ship, you all need to shout after 3, geologize.
No, they don't need to shout geologize, I just need to press a button.
No, it's all part of the wibbly-wobbly, timey-wimey thing. You have to shout geologize.
Alright then, let's shout geologize.
3, 2, 1, geologize! Oh, we nearly there. Oh, yes, we're there,
Okay.
we're there. Oh, great. Okay, we've arrived.
I'm
Excellent.
not really convinced that we're here. I'm just going to check outside.
Okay, I'm sure we have. I'm sure there'll be sort of,
I
dinosaurs
think
and...
we're still in Cambridge. All the buildings look the same. It's all
Well,
the same.
Cambridge hasn't changed in a long time, really.
Well, I've also got a newspaper and it's got today's date on it, so I'm pretty sure we've not travelled in time.
So it's still 2017?
Yeah.
And Trump's still president?
Yeah. What are we going to tell Alan? We can't find out what these rocks are now. We're going to get fired.
No. Well, no. If we're going to get fired, we're not going to be able to pay off our student debts, and then we'll never find out how the rocks formed. Well, think about the rocks.
Matthew, we can still work this out. I'm sure we can solve this. We've got this amazing crew here to help us.
I guess. And yes, you're going to help us, aren't you? You're going to help us keep our jobs? Yeah. Let's do this thing.
Okay, so we've got to work out where, when and how these rocks formed, and we can't travel back in time. So we've got to use the evidence that we've got in front of us in the here and now.
So, our colleagues went trekking in the great outdoors and they found 3 different types of rock in 3 different layers. And we've got them over here. Okay, sorry. And we've also got our assignment guides. Ooh, in-universe reason for having scripts. Which we will use the wonders of modern technology to put things on the screen for you to look at. Okay, so firstly, we've got a pebbly rock, which is, yes, grey and pebbly. We're going to call that rock A to start off with. Then we've got rock B, which is quite dark and silty. And finally, rock C, which is red and sandy. And we need to work out how and when each of these rocks formed.
Well, the pebbly rock, rock A, was found in the bottom layer. So it must have formed first. Then the dark rock, rock B, because it's on top of it, in the middle layer, and then finally the red rock, the sandy rock, rock C, is on top.
So these are sedimentary rocks, and they form by particles of sediment falling down, collecting together. That sediment could be sand or pebbles or organic material, and they fused together to form these rocks. And the layers of sedimentary rocks, they would have taken thousands or millions of years to form.
Yeah, and so the lowest layer of rock must have formed first because it was buried beneath the others. So it must have already been there when the next sediments came to form those rocks, the next layer B, and by the same logic, C must have formed last after A and B because layers A and B are buried underneath layer C.
Excellent. So A formed first, then B, then C.
But it gets a bit more complicated than that. It says here in the assignment guide that while our specimens were taken for 3 layers that were arranged like this vertically, we did in other places find layer A, this rock here, on top of all the other rocks. So that's a bit confusing.
No, that confuses everything. I don't understand.
Well, maybe these rocks were rearranged due to something called faulting.
Ah, faulting, okay. I think I know what faulting is. So, in the Earth, when the rocks are put under a lot of stress, then suddenly those rocks break and the cause a fault, and the rocks on either side of the fault slip past each other. And because of the friction between those two sides of the fault, that makes the Earth shake, and that's an earthquake. But what's that got to do with rocks being the wrong way around?
Well, if there are lots of earthquakes on one fault, the rocks can move large distances past each other, sometimes hundreds of meters, and this could be why we sometimes see our layers in a different order. It could rearrange things.
Okay, I still don't quite understand.
Well, lucky for you, I've got the cake that you made earlier under here, and isn't it lucky that it's got exactly the same structure as our layers of rock?
Mary Berry would be proud.
So imagine that the bottom layer on here is the oldest layer of rock, okay? Then the middle layer is layer B, and the top layer is the youngest layer of rock, layer C. So if we make a fault in the rock like this, I wasn't expecting the cake to make that noise, and then we have lots of earthquakes, then the rocks could move like this, so that they're in a different order than what we expected.
And then if I erode off the top, ooh, here's some erosion, here's some erosion.
I think what Matthew's trying to say is that now we can see that the oldest layer of rock is actually on the top and above the youngest layer of rock. So we can't just always use the vertical heights that we find these rocks in the field to understand their relative ages, because they could have been moved around by faulting along these fault planes, just like we showed on this cake.
Sorry. Yes, I think now I understand. So, even though rock A is on the top, it's only being moved there by faulting, so it's still actually the oldest.
Yeah, that's pretty much right. But it's not always that simple. Rocks don't always break when they're put under a lot of stress. Sometimes they can get squashed and folded, and even turned upside down. I don't know how to show you that. I think maybe I need something like Play-Doh.
Ooh, other modelling clay brands are available. Well, good, because I have got my toy box. Excellent. Okay, what have we got in here? We've got inflatable Dalek, great. We've got a lightsaber. That's useful, but not today. And this is my raccoon that I've had since I was born, and I've taken it all over the world. Don't need that. Okay. Here it is. Here's this.
Oh, again, conveniently made into our 3 rock layers. That was very convenient. So here we go again. Here we've got our 3 layers of rock. And applying a force to rocks like this, sometimes it faults it like we saw before, but sometimes it can cause it to bend into funny shapes. But why would that cause us a problem here? Well, sometimes it could bend like this, and then it could rotate. And if you saw the rocks in the field like this, it might be really confusing, because these 3 layers of rock appear to be upside down.
Yeah, so if you didn't know the original way the rocks were, you could think that maybe this time A was the youngest and C was the oldest, rather than the other way around. So how would you find out which was the right way around?
Well, sometimes there are other clues in rocks that you can use to tell which way up they should be. For example, if an ancient creature made a burrow in the rock, we know that things burrow downwards, so that could really help.
Okay, so if the rocks turned upside down, but you knew the way that the burrow was going when it was first made, you would know that it was actually overturned. So then you'd be able to work out which was the right way up when it was originally formed.
Yeah.
Excellent. Okay, so now we're pretty sure we know the relative ages. We know that A formed first, then B, then C.
But
Right.
that's, yeah, I mean, that's pretty much right, but it's not good enough for our boss, Alan. I mean, he's a really scary guy and he needs high standards or we might get fired. So we need to know the exact ages of the rocks. We know that rocks can be really, really old, millions and billions of years, but when did these ones form? Hundreds of thousand years, millions of years, billions of years ago? I do know one way that we could work this out. It's called uranium-lead dating. Do you know if any of these rocks have uranium in them?
Well, it says here in the assignment guide that they found bands of rock between each of the 3 layers, and this rock was made out of ash. So, say a volcano explodes, puts out lots of ash into the atmosphere, then it falls to the ground whilst all the other sedimentary rocks are forming, and it forms these layers in between. And if you can date those rocks, then you could work out the ages of the rocks either side of them. So, and these have uranium in, so that's good.
So that's great. So we've got something with uranium in. The important thing about uranium for this is that it's radioactive.
Radioactive? Isn't that dangerous?
Oh, well, yeah, but don't worry, because these only have very small traces of uranium in, so we're going to be fine. We're all fine. It's all fine. Yeah, so uranium is an unstable element which decays over time to form a different element called lead. This means that uranium atoms essentially decrease and the amount of lead will increase over time. Measuring the amount of uranium left and the amount of lead that is built up can therefore tell us how old these rocks are. So if there's loads of uranium compared to very little lead, it means that we haven't had a lot of time that's passed for this uranium to decay to lead. But if there's not very much uranium left and loads of lead, we know that loads of time has passed because it's all decayed. So we can use this to calculate the age of the rock. So it takes a set amount of time for half of the uranium atoms in these rocks to decay to lead. And this is called the half-life of uranium. And we can use it to calculate the exact ages of the rocks if we know the amounts of uranium and lead.
Excellent. I think I just about understand that, but I think we can explain it in another way. So, do you think these guys could help us out?
Could you help us out with this?
Okie dokie. Now, I want you all to wave your hands in the air. And don't do it too much because you're going to be doing it for a while. Okay, now you are all uranium atoms, okay? And you are all very radioactive. And you have a half-life of 5 seconds. So after 5 seconds, I'm going to count down, and then half of you, so everyone on this side of me is going to put their hands down, because that means you've decayed into lead and you're not radioactive anymore. Okay, so 1, 2, 3, 4, 5. This half of the room, put your hands down. Keep going, guys, you're still radioactive. Okay, so 1 half-life down. Now, if I go up here, can everyone who is below me, this side, after 5 I want you to decay, but you guys keep going, okay? 1, 2, 3, 4, 5, decay. Okay, and if I keep going, we need another half-life. Okay, people below me here, after 5, 1, 2, 3, 4, 5, down. Okay, and okay, one last line, one more half-life. Okay, after 5 I want everyone on this side to decay. Okay, 5, 4, 3, 2, 1, decay. Woo! You guys can stop now too.
That was really impressive. I don't think I could hold my hands up in the air for that long.
Yeah.
While you and yeah.
So yeah, that's great. So in that demonstration, you guys that you went on for 4 times 5 seconds, so 4 half-lives. So that's 20 seconds. So I know that 20 seconds ago you started being all radioactive. The same thing works with uranium and lead dating, except their half-life isn't 5 seconds, it's 4.5 billion years. And once we've worked out the ratio, so the difference between the how much of the lead there is in relation to the uranium, then we can work out the time.
Well, while you and the wonderful crew were demonstrating the principles of uranium lead dating, in a feat of science, I managed to run all of our rocks through the analyzer, and I worked out their uranium and lead concentrations. So now, using the principles we just talked about, we can calculate their ages using graphs like this, and therefore we know the approximate ages of the rocks. So we can show them on here. So rock A, the pebbly one, formed in a time period called the Devonian, which is about 370 million years ago.
And then rock B, the dark coloured one, which is all silty and weird, and that formed in the Carboniferous period, which is about 320 million years ago.
And then finally, rock C, the sandy one, formed within the Permian period about 280 million years ago.
Excellent. So now we know exactly when these rocks formed and when they formed relative to each other, but wait, we don't know how they formed. How are we possibly going to work out how they formed without going back and seeing them being formed?
Don't worry, we're not going to get far just yet. Perhaps there are hints to how these rocks formed within the rocks themselves. Should we have a closer look?
Excellent. Okay, so let's first look at rock A, the grey and pebbly one. I mean, I can see sort of some grey, sandy bits maybe there. I mean, sand that's found in deserts. Did it form in a desert or something?
But look at these huge pebbles. Do you really think the wind will be strong enough to blow these around? Don't you need something stronger to move those into this rock?
Okay, so you need a stronger thing, like a big rushing river or a big sort of landslide or something.
Well, the pebbles are quite smooth and rounded, so that suggests they've been transported a long way, bashed about and smoothed down over a long period of time. So I would say it's probably a river, not a landslide, because a landslide's just a one for them. So I think we can pretty confidently say it's formed a river.
A river, okay, excellent. So that's rock A. So we have development and we think it formed in a river because of the round place. But what about rock B? That is very dark, it's some weird patterns in. What's going on there?
Yeah, it's weird. Well, often dark-coloured sedimentary rocks have a lot of organic material and really fine-grained sediment called soot in them.
So organic material is like plant stuff and animals and microby things, yeah?
Yeah, that's right. And this pattern, I think it's some kind of bark or the stem of an ancient tree. Plants like these grew in swamps in the Carboniferous period, like wetland swamp areas. So, you know, maybe it formed in one of these.
Yeah, and if there were lots of plants and animals around, a swamp would be a perfect environment both for them living and also preserving them in the rocks. So maybe we formed there. Is there anything more in the assignment guys?
Yeah, in the rocks of a similar age, we found these weird millipede tracks here.
Oh yeah. So can you see those little footprints in the sort of silty rock there? And try and point that out to you. Yeah. And if you actually calculated how big that creature would have been, at 2 meters, so that's as tall as I am, but like now. And so it would have been massive, a massive millipede. That's cool.
So there was lots of life around, you know, when this rock formed, because it's dark, it's got organic material, it's got plant patterns on it, and we found trace fossils of giant millipedes. So that's pretty cool.
Excellent. Okay, so I think we've done A, we've done B. What about C then?
Ooh, well, this one's pretty sandy, isn't it?
Yes, and maybe this one formed in a desert?
Yeah, I think that's a pretty good interpretation. It's completely full of sand. Okay.
Okay, is there anything else about this in the assignment?
Yeah, I mean, we actually found this sample, something called fulgurite here, from a similar place. It's a sort of tube.
Okay. I think we need some help from the audience to try and work out what this is. So if you want to volunteer, please raise your hand. Okay, you look very keen. What's your name? Lucy. Give a big round of applause to Lucy. So, very, very careful. This is very precious. But can you see that tube? Can you go through there? Okay. Could you sort of feel the outside? What does that feel like? Yeah, say it again.
Rough and bumpy.
Very rough and bumpy. But what about just inside? Try not to get your finger caught. What's
Really smooth and soft.
smooth and soft and glassy? Excellent. Excellent deduction skills. You'll make a geologist there. Yes. Well done. Another round of applause for Lucy.
So this tube of rock is rough on the outside and smooth on the inside, and it seems to be made up of lots of grains of sand all fused together. So what would have been so hot and precise that it would strike the sand and fuse it together into this tube? We've got some.
Oh, we've got some.
Yeah.
Let's go off script.
Go on.
Lightning. Oh, excellent.
Oh, perfect.
I think
Exactly.
could lightning be that hot that if a lightning bolt hit the sand, would it be hot enough to fuse it together and form this tube?
Yeah, when a lightning sand's surface, it vaporizes the stuff in the middle because it's so hot, and that's why it's a tube. And then the stuff on the inside is melted sand, so it's glass, and then the stuff around it just gets stuck to it. So this is a fossilized lightning strike.
This is a piece of fossilized. I am Zeus.
Okay. So we can tell that these Permian age rocks formed in the desert. We've seen our sandy bit there. And so it must be mostly dry, but we know that there are big storms which produce lightning because we've got these fossilized lightning strikes.
Excellent. So I think we've actually worked out what all these rocks are. So should we go back through to make sure all of you guys know what these rocks are and make sure you've been paying attention? Okay, so let's start off with rock A. So this was pebbly, had a bit of sand in between, but the pebbles were round. And what type of environment would this have formed in? After 3, 2, 1. Yeah. Excellent, well done, crew.
And this one, rock B, this one, it was dark, it was silty, had lots of organic material, and it's got a pattern on it that's probably from the bark or the stem of the tree. And this formed in a swamp. Brilliant.
Brilliant. And finally, rock C, we think it's formed in a desert because it's all sandy, but then we found a piece of fulgurite, which is a piece of fossilized lightning. Oh, guys, you are amazing. So I think we've done it. I think we've found out how these rocks are formed, and we're not going to lose our jobs. And we couldn't have done it without our amazing audience.
Mild peril has been averted, but I'm a bit disappointed that we didn't actually get to travel in time.
Well, I guess this is what you've sort of shown me through all this. You've shown me you can use all these different techniques, which mean that we can work out when these rocks formed, how they formed, and we don't actually need to go back in time to see them. So I think geology is a bit like travelling in time. And you know what? I think I feel a song coming on. You can join in on the chorus, which we'll sing a few times. Get ready, okay. Okay. Time just keeps on passing from the day it began. And you know that time and tide it waits for no man. You can't turn back the hands of time no matter how fast you run. But you know that time can fly when you're having fun.
But our boss really wants to know when these rocks formed long ago.
So we had to travel back,
So we don't get the sack.
we built a ship to geologize, but it didn't work.
Big surprise.
We're gonna get our pay rise today. We got 3 types of rock, pebble, silt and sand. Investigated further, saw our knowledge expand. We thought we found their ages from their relative heights, but the vaulting and the boarding meant that's not quite right.
And we found another way. Radioactive decay.
We needed help from you.
Our wonderful crew. We waved our hands up in the air. It's how we're watching, I don't care. We found the ages,
Oh yeah, oh yeah.
Geology's like traveling in time. Arriving late to the scene of a crime. We pieced together the story, now we're making it rhyme. And we kept our jokes because geology's like traveling in time. Rounded and smooth pebble show. This rock formed from a river's flow. The next rock was so dark and a land left its mark.
We found a sample of fulgurite. It's an ancient lightning strike. We've
Solve
solved
the mystery, drop the mic, oh
yeah. Oh yeah.
Geology's like traveling in time. Arriving late to the scene of a crime. We pieced together the story, now we're making it rhyme. And we kept our jokes because geology's like traveling in time.
One more time.
Geology's like traveling in time.